Yes. So we are discussing this bending by terminal loads. So let me just present a summary of the equation here. So summary. So we have this equation that del square phi is equal to minus 2g nu times kappa y times x minus dg by dx plus 2g nu times kappa x times y minus df by dy minus 2g alpha. And we saw that the phi can be taken to be 0 on the cross section. So let me just draw this cross section, and then this is the x axis, y axis, and we saw that if half of e kappa x square minus f of y times dy by ds is equal to 0, and half of e kappa y square plus g of x times dx by ds is equal to 0 on C, then this will imply that phi equal to 0 on C. And so if we can choose your f of y and q of x in such a manner, then we get phi equal to 0 on this one. And we also have an equation for determining the alpha. So that equation is given by x0 times wy minus y0 times wx is equal to integral of 2 phi times 2 phi minus e kappa x times x square y plus e times kappa y times xy square. So this times dA. This is for A. So this is used to determine alpha. To determine alpha, and we saw last time that this alpha is a measure of twisting of the cross section. So I gave an example, right? So suppose if you have a C type cross section like this, and then if you apply, so there is a certain point known as the shear center or center of flexure. So if you apply the load through that particular point, then it will simply bend. But if you now apply the load at a certain offset from this shear center, then there is twisting of the cross section. So like this. Okay, so then you can see this the cross section will twist in addition to bending. Okay, so we are going to discuss this concept of the shear center or center of flexure today, based on this alpha value basically. Okay, so let us continue on that particular discussion here. So let us now define the shear center now. So the center of flexure or shear center is defined as the load point x CF, y CF, L, for which the mean twist alpha is 0. Okay. So here I have indicated an example for this C cross section, right? So there is a certain point here which is the shear center. So if the resultant load passes through this shear center, then there is no twisting of this cross section. So that means this alpha will be 0 in that particular particular case. So if you want to now our goal is to find out the location of that shear center there. So so what we do is that in this particular expression, now wherever this x0 y0 is the point of application of the load. Remember that. So this is just so basically we have having this wx and wy, and this distance was x0, right? And then this distance was y0. So now so basically the resultant load will now pass through the shear center, and then your phi is determined such that your alpha is equal to 0, right? So basically set alpha equal to 0, then find phi from this particular equation, then substitute that phi into this particular equation, and then that will give you the shear center. So basically we will write this as xcf times wy minus ycf times wx is equal to integral of 2 phi minus e kappa x times x square y plus e kappa y times x y square times b. So this is with alpha equal to 0, determine phi. Okay. And then so put alpha equal to 0 in this equation. Determine what the phi is with this equation and this particular boundary condition. Then whatever phi you get, you substitute it into this, and then from that you will get the expressions for this one. So so now this okay, so we need these quantities, and so there is only one equation, but we can use the fact that wx and wy can be applied independent of each other, right? And so so first set wx and then wy to 0. So setting wx and then wy to 0, right? We'll get let's write it here. We'll get that xcf is equal to integral of 2 phi by wy minus I xy by I xx I yy minus I xy square times x square y plus I yy divided by I xx I yy minus I xy square times x y square, the whole thing times dA, and similarly you will get ycf, that is the center of flexure of the y component of that is equal to 2 phi divided by wx minus ixx divided by ixx iy minus ixy square times x square y plus ixy divided by ixx iy minus ixy square times xy square, the whole thing times dA. So yes, so so actually it may appear that your shear center depends on the load. It may appear like that from this particular equation, because you can see that wx is appearing in this equation. But what you have to note is that in this particular case, your phi will be proportional to wy. So actually it will cancel. So finally, and then even in this particular case, the phi will be proportional to wx, and then that will also cancel. So finally, the shear center does not depend on the magnitude of the load. Okay, it's just a property of the cross section and the material properties, like the Poisson ratio. Okay, so that is something that you have to remember. So so the shear center is determined. So the shear center is determined by the shape of the cross section and nu alone. So nu is the Poisson ratio, so it doesn't actually even depend on E also. So if the material is homogeneous, then in that particular case it doesn't depend on E also, depends only on the Poisson ratio and the shape of the cross section. Because as I already mentioned, the phi will be proportional to Wi and they will get cancelled. And these other things, as you can see, they are dependent only on the cross sectional properties. And so that is why you will get that the shear center is only a function of the cross section here. So if the cross section is symmetric about the y-axis, so if the cross section is symmetric about the y-axis, then can show that XCF is equal to 0. So let us take an example. So suppose if your cross section is like this. Sorry, this is sorry, not in this way. Let me take it. Let me take another example here. Let me take it like this. And then now this is your x-axis. So now it is symmetric about the y-axis. Then XCF will be 0. So the shear center will lie somewhere along this particular line. Right? So the XCF in that particular case will be 0. Similarly, if you have a cross section that is symmetric about the y-axis, then YCF will be 0. So here in this particular case, you can see that it is symmetric about the x-axis, this particular cross section. Then it is clear that the shear center will lie somewhere along this particular line. But we don't know where along that line, that we have to determine. But it will lie on this line. So YCF will be equal to 0. So here similarly, so if the cross section is symmetric about the x-axis, right, then YCF will be 0. YCF is equal to 0 in that particular case. And if it is doubly symmetric, then it will lie at the centroid itself. So suppose if you have a rectangular cross section, then it will lie, the shear center will lie at the center itself, because then that is at the intersection of the two symmetry axes. So obviously that will be the centroid itself. So the shear center need not be a physical point, like as you can see here, right? So here it's basically the point can lie outside the cross section here, as you can see here. Right? So it's a fictitious point. So the resultant of so there is some distribution of tractions that you are applying on this particular part here, right? On this particular face. And if the resultant of that particular traction distribution is passing through this shear center, then it will not twist. Okay, so that is why this shear center can lie outside the cross section. It need not be a physical point on the cross section here. Fine. So let us now look at the displacements and so on. Displacement field here. So in this particular case here, so suppose if we take this C-type cross section here, okay. Then this is, suppose if this is the shear center and then you are applying the load. So suppose if you apply a load which is offset from the shear center, then you can split this problem into two parts. So one part is that there is a torque which is this distance times this load. Okay, so that will be like a torque, and plus then you can shift this load here and then apply this particular moment here. So you can split this problem into a problem of pure bending, not exactly pure bending, but bending with no twisting. So that means the load is passing through the shear center plus a torque. Okay, so you are basically just shifting this load here and applying a torque here. So you can split this problem into that one. So can resolve. So can resolve the general flexure problem. Into a bending problem, this is with alpha equal to 0. Alpha equal to 0. So you are just shifting this load here and applying a moment. So then and a torsion problem and we need not do this also. We can directly solve it using the equations that we have. So it depends. Whatever you find convenient, you can either solve a problem in this particular way or directly by this one here. So and the torsion problem, or we can solve it directly. So I would prefer this direct approach actually, because then you don't need to do this splitting into bending and torsion. But physically it helps to visualize what is happening. So if you can think about this problem here as a bending problem plus a torsion problem, because if you are applying the load through this, as I said, there will be a twisting of the cross section here. So that's why. Or we can solve it directly using the equations. Directly. And just like we had a neutral plane in the case of the torsion, in the same way we have a neutral plane even here. So let us find out what this neutral plane is. So that is the plane along which tau zz is 0. So that same thing. So let us write that. So neutral plane. So that is tau z equal to 0, and we will get that tan beta is equal to y by x. So that is equal to minus kappa x by kappa y, that is equal to minus ixx wx plus ixy wy divided by ixy wx plus iyy times wy. So and as usual, this beta can be different than the angle subtended by the resultant load. So that's so here, for example, suppose if you take this particular cross section, the resultant load could be at some angle. So W could be at some angle. So let us call this. So this is your x-axis. So this could be at some angle alpha, and the neutral plane could be along some other angle beta. So this is exactly similar to the pure bending problem, where the neutral plane angle was not necessarily equal to the angle made by the resultant moment. So in this case, it's the resultant load. So the angle need not be the same. So beta need not be the same. Beta need not be the same as alpha. Which is equal to tan inverse of Wy by Wx. So that is the angle made by the resultant load. So those two angles could be different as indicated there. Yes, so now we will look at the displacement field now. Integrate the strain displacement relations. So what you will get under the boundary conditions, so again you need to suppress the rigid body motion, so that is done by ux equal to uy equal to uz is equal to del ux by del z is equal to del uy by del z is equal to del uy by del x equal to 0 at x, y, z equal to 0. Okay, so that is at the left end of the beam. So this is your beam and then there is some node here. So at this particular point, you are imposing all these 6 boundary conditions to suppress the rigid body motion. And so the final expressions I will just present for the displacement field. So you will get that ux is equal to minus alpha yz plus kappa x times half of mu times L minus Z times x square minus y square minus 1 by 6 times Z cube plus LZ square by 2 plus kappa y times mu times L minus Z times xy. So this is the expression for ux. And then similarly for uy, you will get alpha xz plus kappa x times mu times L minus Z xy plus kappa y times half of mu times L minus Z times xy square minus x square minus Z cube by 6 plus LZ square by 2. So this is the expression for uy, and then uz is equal to half of z square minus lz times kappa x times x plus kappa y times y plus chi of x comma y minus 1/4 of kappa x times x plus kappa y times y times x square plus y square. So I will come to this. So this function is a function to be determined. Okay, so I will come to this particular point. But these displacements are completely determined if you give me wx and wy. Okay, so there is no ambiguity about finding these displacements components, but here we need to determine this function chi of x of y. And then your tau xz divided by g is minus alpha y plus del chi by del x minus kappa x by 4 times 3x square plus y square plus 2 nu times x square minus y square minus kappa y xy by 2 times 1 plus 2 nu, and tau yz by g. So tau yz by g is equal to alpha x plus del chi by del y minus kappa x times x y divided by 2 times 1 plus 2 nu minus kappa y by 4 times x square plus 3y square plus 2 nu times y square minus x square. So this is the expression for tau yz, and tau zz, finally tau zz is equal to minus e times L minus z times kappa xx plus kappa y times y. So you can see that this new function has now entered into the formulation. So the displacement uz is dependent on this chi and also these stresses. The tau xz and the tau yz are also dependent on this function chi. So let us now talk about this new function that has been introduced. So the governing equation for this new function chi is given by just, it's a harmonic function. So let us write that here. So the governing equation is this del square chi is equal to 0, and the boundary condition is n dot tau c is equal to 0, where this tau c is equal to tau xz and tau yz. So basically what you do is that you first solve this del square chi to 0 and then find the constants in that function such that this tau xz times nx plus tau yz times ny is equal to 0. So that is the traction free boundary condition for the lateral surface here. Okay. So let me just summarize the two approaches here. So if you recall, in the torsion problem also we had several functions, right? One was the warping function, okay, and we also had the Prandtl stress function phi. Okay, so even in this bending problem, now the function phi, which I had introduced earlier, is analogous to the Prandtl stress function, and this function chi is analogous to the warping function. So let me just write that analogy here. So torsion, and this is bending now, and so this is the warping function. So warping xi is analogous to this chi function, or chi of xy in the bending case, and then you have to add the Prandtl stress function, so that was phi, that is analogous to this phi of xy, which I had introduced earlier, right? That del square phi equation that I wrote at the beginning of this class. So that is exactly analogous to this particular thing. So let me summarize now the situation for this bending by terminal load. So either you can formulate the problem in terms of this function phi, yeah? So that equation del square phi and so on, but there is a catch there, that the catch is that only when those two conditions are satisfied, right, which involve that dy by ds and dx by ds, only when those two conditions are satisfied will the boundary condition get simplified to phi equal to 0. But that we may not be able to do for all types of cross sections. So that was very explicitly mentioned. So that we can do only for certain types of cross sections. Okay, so this approach can be used if we can reduce the boundary condition to phi equal to 0. Okay, otherwise it is very cumbersome to use this particular approach. But this approach is much more general, and then the governing. So we can apply this particular approach to any type of cross section. But the boundary condition is much more complicated, because you will see that this tau xz and tau yz, they involve this chi in a complicated way, and hence you can see that when you try to apply this particular boundary condition, it is much more complicated here. But the governing equation for chi is quite simple, just a harmonic function, as I said. So I mean, one can use either of these two approaches. Just like in the case of torsion, we could have used the warping function or the Prandtl stress function. We could have found either of them, and then once you find out phi, then you can find out xi. Or if you first found out xi, then you can find out phi. In the same way, here also, you can either work with this phi or you can work with the chi. So both these approaches you should be familiar with it. Let me start by giving some the displacement by for the centroidal axis now. So based on this, let us simplify those expressions here. See this particular thing here. So from the centroidal now. You will get that ux is equal to kappa x times z square divided by 6 times 3l minus z. Then uy is equal to kappa y times z square divided by 6 times 3l minus z. And the maximum deflection will occur at z equal to L. So maximum deflection occurs at z equal to L. So let us find that equation now. So you will get that ux at z equal to L is equal to kappa x times L cube divided by 3, which is equal to I xx times wx plus I xy times wy times L cube divided by 3e times I xx I yy minus I xy square, and uy at z equal to L is equal to kappa y L cube divided by 3, which is equal to I xy times wx plus I yy times wy times L cube divided by 3e times I xx I yy minus I xy squared. And so now this special case where the axis coincide with the principal axis, then what you will get? So then in that case your I xy will go to 0. So when x and y are principal axis, then in that case you will get that ux at z equal to L is equal to wx L cube divided by 3e yy, and uy at z equal to L is equal to wy times L cube divided by 3e I xx. And so you will see that these formulae are exactly the formulae that you have learned in your strength of materials, right? You must have learned this PL cube by 3EI, right? The U delta, this expression, right? That is exactly analogous to this particular expression here. So, but the thing to be remembered here is that this is only the deflection of the center line itself. So there is a variation in the displacements as you go away from the center line, but still this particular formula will still be a very good approximation to the exact formula also. So there, I mean, if you recall in your strength of materials, we are assuming that the entire beam is bending in the same way as the center line. But here, in the more exact theory, we are assuming that there is a variation in the displacements across the cross section here. And so, the formulae that you get here are only for the center line and they match with your strength of material solution here. So you know, basically what this whole analysis shows is that the strength of materials approximations that we have obtained are very good approximations, because you can see that even from the exact theory you get very similar formulae to what you have learned in your strength of material solutions, right? So all right, so then now let us look at the radii of curvature. So the radii of curvature of the centroidal line, radii of curvature of the centroidal line in the xz and yz planes. So those are Rx and Ry. Rx and Ry. So that is 1 by Rx is del square Ux by del Z square is L minus Z times kappa x, and 1 by Ry is approximately del square Uy by del Z square, that is equal to L minus Z times kappa y. And so that is the reason that this terminology kappa x is justified, because it is like a curvature. I mean, it is not exactly the curvature because there is this factor of L minus Z, but it is proportional to the curvature. I mean, if you do not consider this factor L minus Z, then it is exactly like the curvature here. Okay, so that justifies. So basically, these formulae justify the use of this terminology kappa x and kappa y, because as you can see, they are proportional to the curvature here. And so let us simplify these particular expressions here. So kappa x, we know what that is. So this is now equal to, so let me just write that formula here. Yeah, so if you substitute for this kappa x, del square Ux by del Z square, so you will get minus Ixy times Mx plus Ixx times My divided by E times Ixx minus Ixy square. Now where this Mx and My, so Mx is equal to minus Wy times L minus Z, and My is equal to Wx times L minus Z. Okay, and so this is the expression that you get, and you can simplify this as 1 by E times I inverse times M, the y component of that. And then similarly, you will get for 1 by Ry, so that is your L minus Z times kappa y, so that if you write it in terms of these moments, then you will get it as minus Iyy times Mx plus Ixy times My divided by E times Ixx Iyy minus Ixy square. And so this can be written as minus 1 by E times I inverse of M, the x component of that. So this is that moment of inertia tensor, the inverse of that, multiplied by this M. M is just this vector Mx, My, and then you take the x component of that particular thing. Here you take the y component of that particular thing. So that will give you this expressions for 1 by Rx and 1 by Ry. So basically, what we have shown is that so what we have shown is that so suppose this is the same as your Bernoulli Euler law, right? So this is the same as so this shows that the Bernoulli Euler law is valid. So this Bernoulli-Euler law we had done in the case of pure bending. So that same law is valid even when the bending is taking place by terminal loads. So that is what it says. So shows that the Bernoulli-Euler law is valid even when the bending occurs due to terminal loads. So basically, now suppose if you take x, y as the principal axis, right? So then if x, y are principal axis, then in that case you will see that Ixy is equal to 0, Ixy is equal to 0, and they will reduce to that whatever expression that we had earlier. So that means suppose so in this particular case you will get that Ei del square u by del z square is equal to m. So the usual equation for bending, you will get back that particular equation here. So so basically the same principle that guided us for pure bending can also be used in this particular case when there is bending by terminal loads, because so basically even in this particular case you try to maximize the I, that is the moment of inertia, because that the EI will still be the torsional rigidity. So even in this case, basically what we are saying is that even in this case, try to maximize I, right? Try to maximize I, and so we have seen how to do that, the moment of inertia, so that we, for a given area of cross section we can put it into an I beam, for example, right? So that you move the material away from the neutral axis here, right? So that you can always do. Just one note of caution here. I mean, you cannot carry out this process indefinitely. Okay, so that is something maybe I should just mention at this particular stage here. So let me just illustrate that here. Yes, so I mean, if I keep on sort of distributing the material like this, okay, now next time what I can do is that I can take it even farther away, and then I will have an even thinner section here like this, right? And so I can keep on doing this indefinitely, keep on moving this, and then this will become thinner and thinner because you are trying to maintain the area, same area of cross section. But we cannot do this indefinitely, right? Because I mean, it may appear that just to maximize the I, you can keep on doing this indefinitely, but that is not a good idea, because once this section becomes too thin, then buckling of that section can occur. So that is not accounted for when we are discussing this particular theory. So we cannot keep on continuing this process indefinitely. So there is a limit to how much you can do. So that so you have to bring in other considerations such as buckling also into consideration when you are trying to maximize the flexural rigidity. Okay, so that is something that is also important. So it's a balancing act between the two. I mean, as I said, that the buckling phenomenon we have not accounted for when we are discussing this particular theory, but that is something to be kept in mind. So we cannot just indefinitely keep on increasing this I by simply moving the cross sections away from the neutral axis here. Okay, so in the next class we will look at example problems. So in particular we will look at the elliptical cross section and the rectangular cross section and see how to apply this particular theory and find the exact expressions for the stresses in those particular cases.